So I'm going to go ahead and get to the first practice question now. Well, let me explain one thing first. When looking at percentages and looking at a compound and understanding that a compound is everything that you've got, the idea is that all the elements in the compound, all of their percentages should always add up to the same amount, and that amount is 100. So you can always check your work in this topic by taking all your percentages, adding them up, and seeing if they add up to 100. Now here's the deal. We are always going to round to the nearest 0.1 in calculations. So you may want to write that down. And the reason why I'm saying to write that down is because if you round, your percentages may not add up exactly to 100. So the question is, what's allowable? If I decide to round to the nearest 0.1, which means 39.7, 42.1, 35.8, you may have not a rounding error, but a little estimation. And so if you round to the nearest 0.1, allowable percentages would be between 99.9 and 100.1. And so this accounts for rounding. So allowable percent range would be 99.9 to 100.1%. So this means that if you add up all your numbers and it adds up to 99.9, the question is that close enough to 100 to say you did your work right? Yes, if you round it to the nearest 0.1 for your percentages. If you add everything up and you get 105%, no. If you add everything up and you get 173%, definitely no. And so the idea is that where you're allowed to round to is where you do your rounding. So it's the same idea. If you round to the 0.1, then as long as you're within 0.1 of 100%, you're good to go. If you round to the nearest 1, then anywhere between 99 and 101 would be allowable for adding up all your percentages. But the main idea here is that all your elements' percentages, when you find their mass percent, is always going to add up to 100. Everything that you have. Or else some calculation was done wrong. So I'm going to give you a little bit of time just to write the little notes that I added in. Okay, we're going to go ahead and continue. Here's the first question, and I want you to go ahead and write it down. And I also want you to write down on the side what percent composition is, because sometimes instead of a question asking you for mass percent, they ask you for percent composition. So I'm going to go ahead and define that for you real quick so you understand what the question's asking for. I think I've addressed the word composition before. Composition usually means make something up. And so when we look at composition here, what they're actually asking for is the mass percent of every element in the compound. So underneath percent composition, you're going to want to write what they're actually asking for is the mass percent of every element in the compound. Mass percent of every element that makes up the compound. Every element that makes up the compound. This is what percent composition is. So write that down and then write down the question, and then we're going to go how we can solve this from our first scenario. We've got a 13.6 gram sample of compound, contains only magnesium and oxygen. We know when we decompose it, we get 5.4 grams of oxygen. What is the percent composition of this compound? Now, we've done reactions, so you may have some understanding of what's going on here. I'll explain it shortly, but when you read it, we have actually, and there's a whole entire reason I do reactions before I do this. A lot of teachers choose to cover the math before they cover reactions, but for me it doesn't make sense because you need to understand what you're reading. giving you some time. I want you to write down the question. The first scenario is you've got the data for your math, and you want to figure out what is the percent composition of the elements in the compound. Don't forget that the expectation is you are writing down all practice questions, and that you are, when we work through calculations, you are also calculating in your calculator to make sure that we're getting the same answers. That's for two reasons. First, to make sure you're punching the numbers in your calculator correct. Second, to double check me. It's early in the morning. I'm not immune to making a mistake here or there, punching the wrong number in the calculator. All right, so I'm going to go ahead, and some of you, I feel, already probably know where to go with this, but I want to go ahead and describe what's going on. So we've got a compound that contains magnesium and oxygen. First of all, you actually already know what this compound is, because magnesium is a metal and oxygen is a non-metal. There is literally only one way they can combine. Magnesium has a +2 charge, oxygen has a -2 charge, and this compound has to be MgO. So I'm going to start there. You actually don't have to know this in order to solve the question, but I'm just saying you could interpret this. The next thing, it says that this decomposes. We know what a decomposition reaction is. We know that that means we take the compound and we split it apart, right? So we split it apart to its elements, and they tell you that one of those elements is going to be just oxygen. So let's go ahead and show that real quick. And I'm going to write oxygen in its regular, normal form because that's how it should be written. It doesn't matter to get the question right whether or not you do that or not, but it's just always just to remember. Oxygen is O2. All right, so then the next thing I do is I line up my numbers underneath. I have 13.6 gram sample of a compound. Where does the 13.6 go? Under what? Where would I put that? Under MgO. So under MgO, I'm going to put, okay, I know that that's 13.60 grams. I have 13.60 grams of this compound. That's my massive compound. And then I also know that I have 5.40 grams of, what goes under what? 5.40 grams goes under oxygen. So that's just me thinking about what I'm going to do. Now, in order to calculate the mass percent, I would first calculate this percent composition. I would first calculate the mass percent of oxygen, because I know I have oxygen's mass, and I know I have the compound's mass. So at this point, we should proceed to use the formula I just had you write down, which is to find the percent by mass. You take the mass of the element, you divide by the mass of the compound, and in order to change that to a percentage, you multiply by 100. So we're going to do that now. The formula, just to recall, is mass of element over mass of compound times 100. And that formula is not going to change. It's going to be the same throughout this entire lesson. Even if it looks different, it's the same. Mass of element. So for my percent of oxygen, my mass of element is 5.4. My mass of compound is 13.6. And I multiply by 100. I put the unit in there. You'll notice when you get the percentage, the units cancel. If I've got G on the top and G on the bottom, you can cancel those out. Your percentage has no units. And so 5.4 divided by 13.6 multiplied by 100. We get my calculator. I get 39.7%. The question asks for the percent composition, meaning we want to know what is the percentage of oxygen, and we also want to know what is the percentage of magnesium. So once we get the percentage of oxygen, what could we do next to figure out magnesium? Anybody have any suggestions? That works, and that's the easier way. So if you already know this compound only has 2 elements, you know the percentage of one of those elements is 39.7, right? then the other one must be whatever adds with 39.7 to become 100. So knowing that information, it's really easy to solve for magnesium. You can always find the missing amount that way. So let's do that. So the percentage of magnesium would then be 100 minus 39.7, which is 60.3%. You're the only person, you're the first class that actually came up with that first. In the other classes, I had to bring that up after. Can anybody suggest an alternative method, what the other classes suggested? Is there any other way we could have calculated magnesium using the information that we had besides that statement? And the reason why I'm asking this is just to remind you that when you're solving questions in physical science classes, there is more than one right way. As long as you're making correct relationships and you understand what's going on, there's more than one right way to solve a question. This was one way. What's another? I'm gonna bring it up. If we know that this compound is 13.6 grams, and we know that 5.4 of those grams is oxygen, we also know how many grams is magnesium, right? If this compound is only made of Mg and O, and that's 13.6 grams, and when it decomposes, all the oxygen is 5.4. We could subtract 13.6 minus 5.4 and find the grams of magnesium and then do the formula. So that's the other way. I'm just gonna write it down just so you'll have it. So then the other method would have been to say, oh, 13.6 minus 5.4 is 8.2 grams of magnesium. And then you could do 8.2 for the percent magnesium, divided by 13.6, multiplied by 100, and you will get the exact same answer. For this other technique, what we're using to be able to solve that, my iPad's lagging, sorry. Let's see if it comes back up. Like I've already written all that. Okay, it popped up now. So 13.6 minus 5.4 gives 8.2. Then you do 8.2 grams of magnesium divided by the grams of the compound multiplied by 100. It gives you the same exact answer. What we would be utilizing to solve that is something called law of conservation of mass. The amount that I start with has to be the amount that I end with. You didn't have to use that to solve, but you could. That's question one. Question one is they give you information for the element, they give you information for the compound, and you just plug it in to the formula. This is the less commonly asked question. The most common method of determining the percent composition of a compound is actually using its chemical formula. And so we're going to go ahead and go to that, which is the next scenario. And the one we're going to spend most of our time in. So it's called using molar mass to determine mass percent. You're going to want to title it like this. You can write the formula. It's optional, but it is actually the same formula as before. It's just in the scenario that you have molar mass, here's how you find percent by mass. But it's still, to me, mass of element divided by mass of compound. It's just the mass of the compound, if you're given the chemical formula, is the molar mass. So find the percent composition of Na2SO4, and then on the side, you're going to want to write the practice question. Make sure you write it down. And then I'm going to make a note. If chemical formula is provided, you must use molar mass to find percentages. So if the chemical formula is provided to you, that is what you're going to have to use. You're going to have to use that chemical formula, find the molar mass, and then use that method to find the mass percent of each element in the compound. I'm going to give you a little bit of time to write this down, and then I'm going to show you how I would solve it. If you paid attention last week when I taught how to do molar masses, where I gave a table and I listed out how many elements, how many of each element I had, If you follow that technique, the answer will easily be available to you. So there was a reason why I taught that technique. It's going to have some information that will help you with this process. So go ahead, write it down, and I'm giving a little bit of time before I start solving. All right, so go ahead and write step one. Step one would be to calculate the molar mass. So step one, calculate molar mass. This hopefully is a technique you are getting quite comfortable with. It's something that we're going to do very often in this class. And for most processes, it is the first step in the process. All right, so let's do it for Na2SO4. For Na2SO4, how many sodiums do I have? First question. 2. So 2 times, and we find its mass from the periodic table. From the periodic table, we get 23.0. Sulfur, we only have 1 of them, and its mass from the periodic table is 32.1. And then oxygen, we have 4 of them, and its mass is 16. So that will give us 64. Then we're supposed to add up all of our masses together, and that'll give us the molar mass of the entire compound. So we get 46 plus 32.1 plus 64 is 142.1. And just to recall, that was the amount of grams in a mole of that compound. So that's step 1. Now, think about this. If I think about what molar mass is, this is the mass of my entire compound in a mole of it. I know that out of that mass, 46 grams came from sodium, 32.1 grams were contributed from sulfur, and 64 grams were contributed from oxygen. Is that enough information already to calculate the percentages of each element in the compound? Is that enough info? The numerator would be this amount, and the denominator, which is the whole entire compound, would always be the total, which is the molar mass. So let's go ahead and step 2. Whenever we want percent composition, we want for the whole compound. So step 2 is to find mass percent for all elements. For all elements in the compound. And so we're first going to start with the percentage of sodium. Percentage of sodium. And so if I want the percent of sodium, I would get the mass of sodium in the compound, 46, and divide by the whole compound, which is 142. So 46 on the top and 142.1 on the bottom. And then because we want a percentage, we have to multiply by 100. So it's 46 over 142.1 times 100. You get 32.4%. And then we do the same thing for sulfur. The only number that will change is the top number. How many grams in this compound come from sulfur? So to get the percentage of sulfur in the compound, we look for this number. 32.1 comes from sulfur. So 32.1 would be for the top, and 142 would be for the bottom. So we do 32.1 divided by 142.1 times 100. Once again, you should be checking in your calculator, just making sure you're getting the same answers. I get 22.6%. And then for oxygen, same idea. I want the percentage of oxygen. Oxygen is 64. The whole compound is 142.1, and I multiply by 100. And then what you can do, just to check to see if the work has been done right, is add up your percentages. If these percentages add up to become 100, then you know that your work is on track. This is definitely a process we're going to use a lot, so we're going to practice again. I'm going to show you one that's a little bit harder, and then you'll have one to do yourself. So as always, when I do 3 examples, I always like to show one first by myself. The second one, if you want to try to beat me to the answer, if you feel like you kind of got a handle on what to do here, please feel free to do so. And the third one, you're going to do on your pod. We're going to go to question 2 in about 30 seconds, just so you're aware. All right, we're going to go ahead and move forward now. Let's try the second example. So practice question number 2 on this technique using the molar mass. It is to find the percent composition of every element in Fe2, CO3, 3. Fe2, CO3. So make sure you're writing it down, second practice question. This time, like I said, I kind of like to do this thing where I do the first one, I pause for the second one to give you a little bit of time to work ahead of me, and then for the third one, you're going to do it on your own. So if you're feeling confident in this technique, please go ahead and solve it. This one's a little bit more difficult just because of that parentheses. Don't forget you have to distribute the amount of atoms for the parentheses. We have went over that a lot in the last unit, so hopefully you remember what to do here. I want the percent composition of every element in iron 3 carbonate. Now, I told you for this unit, I'm going to give you the chemical formulas. I'm not going to give it by name for the quiz and the test. That's to make it a little bit easier. However, I do expect you to know if I say iron 3 carbonate, that you know what I'm talking about. This is iron 3 carbonate. Second question, find the percent composition of every element in Fe2, CO3, 3. Work ahead of me if you're feeling comfortable. In about a minute, I'm going to go ahead and start solving it. Same technique as the last question. So remember, step 1 is to calculate the molar mass. And if you set it up as a table, all the numbers you need will be right there in front of you. And so I'm going to go ahead and start solving. I gave a little pause. If you're still working through it, please feel free to. But the reason I paused was to give you time to beat me if that's what you want to do. All right, calculate molar mass. So the first thing we want to do is list out the elements that we have. Then we have to figure out the amounts. The amounts we figure out from the chemical formula. For iron, the amount's going to be 2. So 2 times the mass is going to be from the periodic table. So for iron, that's going to be 55 So I do 2 times 55.8. And the mass from iron is 111.6. Carbon, how many carbons do we have? 3. Because we have to distribute. There's 1 in carbonate, but there's a 3 on the outside, which means that distributes to give us the total amount. So we have 3 carbons, and each one has a mass of 12. So that's going to be 36. And then finally, oxygen, 3 times 3 is 9. So we do 9 times 16, which you do not have to do in your head. You've been using a calculator for all of this, and you get 144. Add up all those masses together, and your total mass is 291.6. So if you were working ahead of me, make sure that that's what you got for your molar mass. After you determine the molar mass, now you find the percentage of each element in the compound. So step 2, find the percentage. Find percent of each element, because that's what percent composition is. So I'm just listing out what my steps are. And so then for iron, and I'm going to list them out in the same order. My percentage of iron is going to be my mass of iron divided by the mass of the compound multiplied by 100. I can find the mass of all my iron in the compound by just simply looking at this number. The one that we calculated, 2 times 55.8, 111.6. So the top for my formula is going to be 111.6. And the bottom, 291.6. 111.6, that's coming from there. And then the bottom is 291.6. And then we multiply that by 100. I get 38.3%. Then I do the percentage of carbon. That's going to be 36 divided by 291.6 multiplied by 100. Is 12.3%. And then for oxygen, the percentage of oxygen is going to be 144 on the top, 291.6 on the bottom, multiplied by 100. And I get 49.4%. Add up all the percentages, see if they add up to 100% or within 0.1 of 100%. They should. And before I move on to the third example, there's something really important. I left this slide mainly blank because there's something I also want to add into the top to fill in for you to add into your notes after this example. And that's really, what does this mean? What does this information even tell us? What does this tell us? And what it's telling us is actually something that's really important for the second half of this lesson, which I told you I was breaking off to a separate day. That's in order to give you a better understanding of each process. I am slowing down a little bit. This is a hefty math unit. What does this even mean? When we say 38.3% of this compound is iron, 12.3% of this compound by mass is carbon, and 49.4% of this compound by mass is oxygen. What is that actually communicating to us? So I'm going to explain that now. So the first thing I want you to do is write at the top 100% Fe2 CO3 3. Go ahead and write that down into your notes. And then what I'm going to ask you to write afterwards is all the percentages for each element. So I'm going to write that out in a line. I know that when I have 100% of my compound, which you always would, that's your whole, that 38.3% of that compound is iron. 12.3% of that compound is carbon, and 49.4% of that compound is oxygen. But what does that even mean? Go back to what the title of the lesson is. Title of the lesson is mass percent. These percentages are mass percent. So what does that mean? So you're going to write a second line. This means that out of every 100 grams of the compound, we can predict exactly how many grams of each element we have. So instead of writing 100%, write 100 grams. Out of every 100 grams, the ratio will be the same. So 100 grams of Fe2CO33. I can now predict, if I have a 100-gram sample of the compound, I know exactly how much of each element I have in that compound. Out of 100 grams, how many grams are iron? You think? Don't think too hard. How many grams? 38.3, right? 38.3 grams are iron. So if I have a 100-gram sample of the compound in front of me that I put in a scale, I know that 38.3 of those grams are iron. Go ahead and write that down. So I know that 38.3 grams are iron. I know 12.3 of those grams are, and 49.4 of those grams are oxygen. Now, what can you do with this information? Remember, I'm all about giving you resources and tools and methods. And there's more than one method to solve the question. These are anything that's an equality can be turned into a conversion. So underneath this, you may want to just write just an example of one. This means that you could turn any of these relationships into conversion factors. They're potential conversion factors if you need it. Meaning, for example, you could say 38.3 grams of Fe is for 100 grams of the compound. Oops. And I'm going to rewrite that without the writing. 38.3 grams of Fe is for 100 grams of the compound. And if this is a conversion factor between a compound and the element within, that means you now have an ability to find the mass of any element within a compound just with elements. And so that's where we will get to very shortly. But before we do that, and I'm giving you a little bit of time if you wanted to write that down. Before we do that, we are going to go ahead and do a practice question on your end. So I did a question. Then I asked you to solve ahead of me if you felt comfortable. Now, I expect you, hopefully, to feel comfortable for this one. Go ahead and find the percent composition for each element in the compound glucose. B6H12O6. So using the same technique that I showed you in the past two questions, if you could do this for glucose. Let me know when I move back forward, okay? I have it on your pod, so make sure that you are spending the next 4 minutes I'm going to give you to write your answer in Nearpod. Make sure you show your process. I am going to show one of your responses that's done correctly to the class in about 4 minutes. You're good? Okay. we do this example, there's one more technique that I need to cover, and then actually we'll have time for classwork today. The goal is, if you can finish the classwork by the end of class, you don't have additional homework, and you are just studying for the quiz that's next class. I will post up practice quizzes for you to be able to use for that. On your pod, please. You've still got a few minutes before I share out an answer. You can also write the answer on your paper and then submit on your pod. You want to have another practice example in your notes. But this example is your turn. Then you'll need to show me your answer on paper. So this tends to be one of the lessons that students find to be one of the easiest, at least this part of the lesson, because it's a very straightforward, hopefully, process. The hardest part of the lesson is what's coming up after this. Okay, so about 30 more seconds. Yes. All right, so I'm going to go ahead and share out one of your responses. Many of you got the answer correct. I know that some of you are still working on it. As long as you had put anything on your pod, like any sort of response that you were working on it, you'll get full credit for participation. I'm sharing with the class one of your responses. This is absolutely correct. So the percentages worked out to be 40% for carbon, 6.7% for oxygen, and 53.3%, 6.7% for hydrogen and 53.3% for oxygen. So very nice. All right, so we have one more thing to talk about, and that's what can we use mass percent for as we're working through conversions? Yes. On your paper? Let me check. Yeah. So the last thing that we have to go over for the day is the following. Calculate the mass of an element when given any mass of a compound. And I'm going to add that the element is in, just to be specific. So we got an element within a compound. We have the total amount of the compound. And please write down the number that's on Google Meets, not on your pod. I changed it because I felt that the amount before was a little bit confusing to students, and you'll see why when we work out the percentages. So I changed the number to make it a little bit more straightforward. Question says, calculate the mass of carbon and calculate the mass of hydrogen when I have 54 grams of propane. So now we've got an amount that's not 100. We've got a different amount. And we want to know from any amount of a compound, could we figure out the mass of the elements within that sample of the compound? That's the final thing we're looking at today. I told you this would be the most difficult process. It takes a little bit of extra thinking. So make sure you're writing down the question. You should write down the title so you know what type of question this is. And then I'll go over the process. Okay. So if I want the mass of an element within a given compound, there is actually more than one way you can use mass percent to solve this. I will show you both, and then you pick which one you prefer. Some students will prefer to work with percentage because if you know how to work with percentages, it's really easy to solve. But if you don't know how to work with percentages, you may want to use another. All right, so here we go. First thing. If I want to know the mass of elements within a compound, the first thing you are going to have to figure out is the percent composition of that, which is how much percent of that compound is carbon and how much percent of that compound is hydrogen. So the first thing you're going to want to do is go through the steps to find percent composition, which means step one is once again to find the molar mass. And throughout most of the rest of this unit, the first step of whatever process we do is usually going to be to find the molar mass. So step one, find the molar mass. Eventually, you'll be finding molar masses like a pro because you'll just keep doing it over and over again. So find the molar mass. We need to find out the molar mass of C3H8. And so this is going to be, I gave one that is not too difficult to figure out, no parentheses. So carbon is 3, I don't know, it keeps going back, times 12 is 36. And hydrogen is 8 times 1 is 8. And then I add 36 and 8, and I get 44. So I know this is my mass of my compound. And I know this is the mass of each element. So step one, find the molar mass. And so I'm going to show you method one. Step two would be to find the percent composition. Step two, find percent composition, which means same formula. 36 over 44 times 100, 8 over 44 times 100. You find the percent of the compound that's made up of carbon, and the percent of the compound that's made up of hydrogen. So step two, find percent composition. For carbon, this is going to be 36 divided by 44 times 100, which is 81.8%. And for hydrogen, it's going to be 8 divided by 44 times 100, which is 18.2%. And then step 3, find mass of each element. So I'm going to show method 1, method 2. I have 54 grams of this compound. So if you think about it, 54 is my total. That equivalates 100%. 100% of my compound, my sample that I have in front of me is 54 grams. I know that 81.8% of the mass is carbon. What would you suggest for a method 1? What would you suggest? How could I figure out the specific amount of grams of carbon in 54 grams of propane? Anybody got an idea? Not divided. Multiplied by it as a decimal, so that you get a fraction of it. So method 1 would be to change the percent to a decimal and literally just multiply that times the total. So I'm going to write that out. So method 1 is the one that you understand percentages and how they work. It's change percent to decimal and multiply by total grams. And so this is going to be for the carbon, it would be 54 grams multiplied by, what is the percentage of carbon? 81.8. So how do I turn that to a decimal? You move that over 2 spots. It's the same thing as saying 81.8 over 100. You have to move the decimal over 2 spots. So you multiply 54 by 0.818. .818. And that would give us 54 times 0.818. So I get 44.2 grams carbon in that 54 gram sample. And so now for hydrogen, I would do 54 multiplied by what? If hydrogen is 18.2%, what would I take my total mass of 54 and multiply by? 0.182, which is basically move your decimal over. That's changing percentage to decimal. Move your decimal over 2 spots to get it to decimal form, and then you just do 54 times 0.182, and that gives you 9.8 grams of hydrogen. Your total grams should add up to what? 44.2 plus 9.8 should add up to 54, and if it doesn't, then there's something done wrong. That's method 1. Method 1 is the one I used because I like that. And I just used what I knew to solve questions. Method 2, I'm just going to show you real quick. For one of the elements, just to show that it gives you the same thing. Method 2 would be to use the mass relationship as conversion. And I'm just going to show you what that looks like, and you may want to have it just in case you don't like to use percentages. The other method is to use the mass relationship as a conversion, which I have right here. The mass relationship. I know that 36 grams of carbon and 8 grams of hydrogen is 44 grams of the compound. That is a relationship. So to do that, our given amount would be 54 grams. Go ahead and write 54 grams of propane. .54 grams C3H8. We do want to specify what it is we have. And the idea is the following. I know that for 44 grams of propane, 36 of those grams are carbon. So I could put 44 grams of propane on the bottom and 36 grams of carbon on the top. And so I do that. So 44 grams propane on the bottom and 36 grams of carbon on the top. And then we put an invisible 1 under 54 and we do the conversion, which is 54 times 36 divided by 44. And if you do the math, you're going to see that it works out to be the exact same answer. And this is just to mention that there are multiple correct ways to solve. If you are to take a Cambridge course that requires problem solving, such as chemistry or AICE mathematics, you must show your steps. It's not that you have to show one way, but you must show your steps. Oftentimes, if they give you a question, it'll be worth something like 3 marks. 2 of those marks are for your steps. There's more than one method you can use, and they will give you marks for it. But if you only write your answer with no steps, the maximum amount you can get is 1 out of 3, believe it or not. So you have to get comfortable with writing out your steps, for those of you who just like plugging numbers in calculators. If you anticipate to move forward to a problem-solving style Cambridge class. It's nice, though, because if you do show your steps and you make a mistake, you can actually get more points for the wrong answer than for the right answer. You can get 2 out of 3 if you make 1 mistake. Whereas if you get the right answer, but you don't show your work, you get 1 out of 3. You get more points for showing your work and making a single mistake than not showing your work. So it's very interesting the way that they assess. All right, let's go ahead and do this again. So question 2, calculate the amount of grams of carbon in 130 grams CCl4. This time, like I said, 3 questions. First question, I do alone. Second question, if you want to beat me to the answer, please feel free. And third question will be yours to do on your own. And then we'll be done with the lesson. Second question, calculate the amount of grams of carbon in 130 grams of CCl4. Use whatever technique you want. That works. Any relationship that makes sense. Yes. Question? Oh, just stretching? Okay. This question, because I added it to give an additional example, it's not in Nearpod, but it is in Google Meet. Calculate the amount of grams of carbon in 130 grams of CCl4. I hope you started to work ahead of me on this one. I'm going to go ahead and start solving it. I'm going to use method 1. That's my preferred method. So step 1, molar mass. Carbon, 1 times 12, 12. Fluorine, 4 times 35.5, 142. 12 plus 142, 154. Then because I'm only looking for carbon, do I care about chlorine? Do I have to do any work for chlorine? No, I just need to do the work for carbon, right? You don't need any information for chlorine because it is not asking about chlorine. So just do what's being asked. I mean, you could do chlorine if you wanted to. Hi.
Hi.
Yes.
Okay.
Working on the AICE.
Awesome.
Yeah.
It is?
Yeah.
I hear it.
Yeah.
You do hear it. Okay.
I can hear the air coming out.
Okay, awesome. Yay. My later classes would have been miserable if it wasn't fixed. I was already feeling bad for sixth period. Okay, so you just need the percent of carbon. You don't need the percent of chlorine here. So I'm going to find the percent of carbon. So step 2, percent of carbon. And so to get that, I would do 12 divided by 154 times 100, which is 12 divided by 154 times 100. And so I get that it's 7.8% carbon. And then to find the grams of carbon, this is step 3. I would just take 130 because this is my total amount. It's 100% of what I have. And I'm just taking 7.8% of that. It's the same question as what is 7.8% of the number? So 130 times 0.078, because you always have to move your decimal over 2 spots, I get 10.1 grams carbon in this compound. See if that makes sense. Now, you actually, by using method 2, might have actually saved some work, just to throw it out there. Using method 2, once you get the molar mass, you have enough information to make a relationship. So if you decided to use method 2, you wouldn't have to do this. Instead, you would just do 130 grams. So I'm just going to show method 2 just so you could see. You can go directly from step 1 to method 2. So method 2 would be start with the 130 grams of CCl4, put it over 1, and then multiply by 154 on the bottom, because that's the whole, and 12 grams on the top. It will give you the same exact answer. And you cancel out the CCl4, and you have grams of carbon. So you choose which one you want to use. If you like working with percentages, then method 1. If you don't like working with percentages, you can use the same techniques we've been using throughout this entire class, which is dimensional analysis, through this entire unit. So your choice. What you want to do is fine. Your turn. So on your pod, there is, and this is the last question for today's lesson. I'll be passing out the homework as you work on this. So this is your exit ticket question for the day. And after you're done with that, you can start to work on the homework. You probably get halfway through it by the end of class, to be honest with you, because it is pretty quick. It's on paper. It's single-sided. There's no back. So it's going to be due at the beginning of next class, but get done what you can by the end of this class. The question I have on Nearpod is for you to calculate the mass of hydrogen contained in 153.5 grams of water, H2O. As you're doing that, I'm passing out the homework. This is going to be due Thursday at the beginning of class. Next class, beginning of class. Here we go. But it was 2 classes ago. You have a paper from molar mass? Did you miss multiple classes? I gave it out on Wednesday. Unit 5, lesson 2. Unit 5, lesson 2 was Wednesday. You don't have this paper? I didn't hand out a paper on Friday this morning. I'm sorry? You can. Once you're done with the Nearpod question up on the screen, when you go to work on the classwork / homework, you may work with someone if you like. Make sure to finish the near-pod question first, though, before moving. That is the exit ticket question for the day. Remember, you're finishing near-pod first, and then once you're done with near-pod, you should start working on the classwork. Once you get to work on the classwork, you can work with a friend or you can work by yourself. I also want to remind you that if you are needing assistance in any of the tutoring assignments from the past week that were assigned, please make sure to stop by for tutoring today. Tutoring is after school. It starts at 2:30, ends at 3:30. I will reveal the answer at 9:10, so you can know if you got it right or not. With whichever method you're using. Just looking for the right answer here. You can use either method, just make sure, like I said, get in the practice of showing your work for whichever method you use. I'm gonna hit stop recording now.